In this video, we're going to use mathematical induction to prove this inequality. n plus 1 less than 3 to the nth. Here n is a positive integer. So n is 1, 2, 3, 4, and so on. So here n starts from 1 and then 2 and 3 all the way to infinity. Mathematical induction has two steps. Step 1, we do the basis step. In this step, we always start with the smallest n. So the smallest n integer for n is 1. So let's say n equals 1. Now let's check the inequality that we need to prove. The left-hand side, plug in 1 for n. So we get 1 plus 1, which is 2. In the right-hand side, we replace the nth power 3 to the n, replace n with 1. So we got 3. And apparently, 3 is less than 2. The left-hand side is less than the right-hand side. So we can say the inequality holds for n equal to 1. Now let's do the inductive step. In the inductive step, we always assume the formula or the inequality in this case. Inequality holds for n equal to k. So in this case, the formula, the inequality we want to prove is n plus 1 less than 3 to the nth. So now this time, in the basis case, we replace n with 1. The left-hand side, we replace this n with 1, and on the right-hand side, we replace this n with 1, and we did find proof the left-hand side is less than the right-hand side. So now in this case, we're gonna, because we assume the inequality holds for n equal to k, so we gotta replace the left side n and right-hand side n with k. So we get k plus 1 less than 3 to the kth. And our goal, let's write down our goal inequality. And the goal is always the formula or inequality for n equal to k plus 1. So we increase this n from k to k plus 1. So which means, so we want to prove the inequality holds for n equal to k plus 1. So what is the inequality if n equals k plus 1? Similar to the previous two cases. Basis case, replace n on both sides with 1. The n equal to k case, we replace n on both sides with k. If n equals k plus 1, of course, so we're going to replace both sides n with k plus 1. So I'm going to write down the formula. The left-hand side will be k plus 1 to replace n. There's another plus 1 on the left-hand side. On the right-hand side, replace n with k plus 1. So this is our goal inequality. That's what we want to prove. K plus 1 is less than 3 to the k plus 1th power. So we start with what we know. This here is what we know, and we want to prove this inequality. Okay, so we try to compare the left-hand sides, see if we can get k plus 1 plus 1. Apparently, we should add 1 to both sides in order to get the left-hand side. So if I add 1 to the left-hand side, k plus 1, that's the original left-hand side. We add plus 1 to the left-hand side, we will get exactly what we need in the goal inequality. On the right-hand side, we're gonna also add 1. So use the red color to describe the one we added. Okay, this we know by the property of inequality. When we add 1, the same number to both sides, the inequality sign does not change. Okay, so we got the left-hand side. They match. This matches that. But the right-hand sides, they don't match. This does not match this. So that is something what we need to work on. So by algebra, I know that 3 to the kth I can replace this number 1. Well, let me use a different color for the second part. So I keep the first part, 3 to the kth and 3 to the kth, without changing these two here, 3 to the kth and 3 to the kth. But I'm going to replace this this plus 1 with plus 3 to the kth. Okay, if we look at the second inequality, and this is apparently true, because the first part, each side has 2 parts, 3 to the k and 3 to the k, they pretty much cancel each other. 1 is less than 3 to k. That's always true because k, so let me put this on the scratch paper. We know 1 is always less than 3 to the kth because k is, the smallest k is 1. And if we replace k with 1, we get 3 to the first. That's 3. 1 is less than 3. Well, for other integers, if k is 2, we got 9. If k is 3, we got 27. This part is going to get larger and larger. The smallest number for 3 to the k is 3. 3 to the first, which is 3. And 1 is already less than the smallest. Of course, 1 is going to be less than all the other integers. So it doesn't matter what k is. This is always true. 1 is always smaller than 3 to the kth. So that's why when I can add 3 to the k to both sides. When we add the same integer to both sides, 3 to the k to the left, 3k to the right, this will stay as less than. So that's how we get this one. The reason I enlarged 1 to 3 to the kth is because 3 to the kth plus 3 to the kth is going to be equal to 3 to the k times 2. Well, I actually need 3 to the k times 3. Why? Because this is what we need. This is going to be, if we use algebra, we know 3 to the k plus 1 equals 3 to the k times 3. So which means we need 3 copies of 3 to the k instead of just 2 copies of 3 to the k. So I'm going to go ahead and add another copy of 3 to the k, because 3 to the k plus 1 is already smaller than 3 to the k plus 3 to the k. If I add another one, it's going to make the right-hand side even larger. And so the left-hand side is still going to be less than that. And now we know this is by using simple math. It's adding 3 copies of 3 to k is like 3 to k times 3. And it's just like if we add x and x and x, we will get x times 3. So instead of having x plus x plus x, we have 3 to the k plus 3 to the k plus 3 to the k, which is 3 to the k times 3. By algebra, multiplying the numbers, the exponents with the same base, we keep the base 3, we add the exponents. So if we just look at the left-hand side, they match, and the right-hand side, they also match now. So we proved k plus 1 is less than, so we're gonna skip all the steps we had, just copy the final right-hand side. We proved the k plus 1 is less than 3 to the k plus 1th power.